It's late at night. The rail yard is almost completely silent. Freight cars sit motionless on the tracks. Signals glow in the distance, and not a single train appears to be leaving. Yet one sound never stops. Somewhere in the darkness, a massive diesel locomotive continues to rumble away. Hour after hour, it burns fuel without moving an inch. Sometimes it sits like that until morning. In extreme cases, it can remain running for several days. If you've ever seen this, you've probably asked yourself the same question. Why doesn't anyone just shut it off? At first glance, it looks like an incredible waste of fuel. The engine is making noise, producing exhaust, and seemingly accomplishing absolutely nothing. But that first impression is misleading. A modern locomotive isn't simply an oversized truck engine. It's closer to a self-contained power plant that happens to ride on steel wheels. The diesel engine isn't only there to make the train move, it also supplies electricity, air pressure, heating, cooling, battery charging, and several critical safety systems. Turn the engine off, and many of those systems begin shutting down with it. That's why something that seems so obvious can quickly become a serious operational problem. And surprisingly, the reason has very little to do with old habits. Instead, it's a combination of engineering, safety, economics, and one enemy railroads have battled for more than a century: cold weather. Over the next few minutes, we'll discover why locomotives often stay running 4 hours, or even days, why restarting one isn't nearly as easy as starting your car, how the braking system depends on compressed air, and why railroads are investing millions of dollars to reduce battling without sacrificing reliability. To understand why locomotives still idle today, we first have to go back to a time before diesel engines even existed. Long before modern locomotives arrived, steam engines faced a similar challenge. Unlike a car, a steam locomotive couldn't simply be switched off at the end of the day. As long as it needed to remain available for service, the fire inside the boiler had to be kept alive. Crews maintained a small but steady fire to preserve steam pressure, prevent parts of the system from cooling too much, and make sure the locomotive could return to work without hours of preparation. Safety also played a role. Railroads had adopted air brakes that relied on compressed air to operate safely. If pressure disappeared, the brakes would automatically apply. Maintaining a locomotive in a ready-to-go condition became part of everyday railroad operations. When diesel-electric locomotives replaced steam during the mid-20th century, the technology changed dramatically. But the operating philosophy didn't. The new engines no longer burned coal or produced steam, yet they still needed electrical power, compressed air, charged batteries, and reliable systems that crews could count on at any moment. Instead of eliminating the need to keep locomotives running, diesel technology simply introduced a different set of reasons. And those reasons all begin with one surprisingly important fact. A locomotive engine isn't just an engine. It's the heart of an entire mobile power station. Prima, we gaan verder met hoofdstuk 2. Hier leggen we uit waarom een diesel-elektrische locomotief veel meer is dan alleen een motor, maar zonder de tekst of opbouw van het voorbeeld te kopiëren. Chapter 2. A power plant on wheels. Most people think a locomotive works like a giant truck. Press the throttle, the engine sends power to the wheels, and the train moves. In reality, that's not what happens at all. A modern diesel locomotive is a diesel-electric machine. The diesel engine almost never drives the wheels directly. Instead, its primary job is to spin a large electrical generator, producing the electricity needed to power the locomotive. That electricity is then sent to powerful traction motors mounted on the axles. Those electric motors, not the diesel engine itself, are what actually turn the wheels. But moving the train is only part of the story. The same electrical system also supports dozens of other components that have nothing to do with acceleration. Air compressors maintain brake pressure. Cooling fans prevent equipment from overheating. Pumps circulate coolant and lubricating oil through the engine. Batteries remain charged so critical electronics stay operational. The cab needs lighting, climate control, communication equipment, and safety systems that remain available even when the locomotive isn't moving. In other words, the locomotive is constantly supplying power to itself. That changes the way railroads think about shutting an engine down. Imagine turning off the generators in a hospital. The lights don't simply go out. Ventilation, monitoring equipment, communications, and countless support systems disappear at the same time. A locomotive works in much the same way. When the diesel engine stops turning, electrical production stops with it. Some equipment can continue operating for a short period using battery power, but batteries were never designed to keep an entire locomotive alive for hours. Their job is to support the system, not replace it. Eventually, battery voltage drops, air pressure begins to fall, temperatures inside the engine start changing, and the locomotive slowly loses the ability to restart itself without outside assistance. That's why railroads don't see an idling locomotive as an engine doing nothing. They see a machine that is actively keeping itself ready for work. Even while standing still, compressors cycle on and off, cooling systems continue circulating fluids, electronic control units monitor the locomotive's condition, and batteries receive a constant charge. All of this consumes energy. Of course, burning diesel while parked isn't ideal. Fuel costs money, engines wear over time, and nearby communities have to live with the constant noise. So why accept those disadvantages? Because under the wrong conditions, shutting the engine down can create a much bigger problem than letting it idle. And nowhere is that more obvious than during winter. As temperatures begin to fall, almost every fluid inside a locomotive starts behaving differently. Oil becomes thicker, diesel fuel flows less easily, batteries lose much of their available power. Even moisture trapped inside the braking system can become a serious threat. For railroads operating in freezing conditions, cold weather isn't just uncomfortable. It's one of the biggest engineering challenges they face. Mooi. Hier is hoofdstuk 3. Dit sluit direct aan op het einde van hoofdstuk 2 en bouwt de spanning verder up. Chapter 3. Why winter changes everything. If you've ever struggled to start your car on a freezing morning, you've already experienced a small part of the problem. Now imagine doing the same thing with a machine that weighs well over 200 tons and is expected to pull thousands of tons of freight the moment it's needed. That's the challenge railroads face every winter. Cold weather affects almost every major system inside a locomotive, and many of those effects begin long before the temperature drops below zero. One of the biggest concerns is the engine's cooling system. Even though locomotives use coolant to protect the engine, operators still need to make sure that coolant keeps circulating. If temperatures become low enough and the coolant sits still for too long, the risk of damage increases dramatically. Pumps, hoses, seals, and radiators are all designed to work within a certain temperature range. Keeping the engine running helps maintain that balance. The fuel itself creates another problem. Diesel isn't exactly the same in every season. Winter diesel is specially blended to perform better in cold temperatures, but even then, extreme cold can cause wax crystals to form inside the fuel. As these crystals grow, they can clog filters and restrict fuel flow. An engine that can't receive enough fuel simply won't run. Lubricating oil creates yet another challenge. When temperatures fall, oil becomes much thicker. That makes it far more difficult to turn over a massive diesel engine during startup. Instead of flowing quickly through bearings and moving parts, cold oil moves slowly, increasing resistance exactly when the starter motor is working its hardest. Then there are the batteries. Most people don't realize just how much electricity it takes to start a locomotive. These engines require an enormous burst of current just to begin turning. Unfortunately, batteries lose a significant amount of their available power in freezing temperatures. As the weather gets colder, they become less capable of delivering the energy needed for a successful start. That creates a dangerous situation. If the batteries don't have enough power, the engine may fail to start. If repeated attempts drain them completely, the locomotive can become stranded exactly where it sits. And unlike a passenger car, you can't simply ask someone for a jump start. A disabled locomotive may require another locomotive to rescue it, delaying crews, blocking tracks, and disrupting traffic across an entire rail network. Even the braking system isn't immune to winter. Tiny amounts of moisture can accumulate inside airlines over time. In freezing conditions, that moisture can turn into ice, interfering with valves or restricting airflow. Railroads work hard to prevent this from happening, but keeping systems warm greatly reduces the risk. When you combine all of these factors, a pattern begins to emerge. cold weather doesn't create one big problem. It creates dozens of smaller problems that all happen at the same time. Thicker oil, weaker batteries, cold fuel, cooling systems under stress, brake components exposed to freezing temperatures. Each issue alone might be manageable. Together, they can leave a locomotive unable to move when it's needed most. That's why many railroads would rather burn fuel overnight than gamble on an engine that refuses to start the next morning. Because if restarting fails, the consequences reach far beyond a single locomotive. One disabled engine can delay an entire freight train, and one delayed freight train can quickly affect rail traffic hundreds of miles away. Top. We hooden to flow vast and bow into spanning verter up. Here is Hoofdstuk 4, Chapter 4, Why Restarting Isn't Always Simple. For most of us, starting a vehicle is something we barely think about. You turn a key or press a button, and within a second or two, the engine comes to life. A locomotive is a completely different story. Everything about it is built on a much larger scale. The engine itself is enormous, with massive internal components that require an incredible amount of force just to begin rotating. That means the starting system has to deliver an enormous burst of electrical power. If the batteries aren't fully charged, or if freezing temperatures have reduced their performance, the starter may not be able to spin the engine fast enough to fire. And that's only the first hurdle. Once the engine starts, it doesn't immediately become ready to pull a train. First, oil pressure has to build throughout the engine to protect moving parts from excessive wear. At the same time, coolant begins circulating, electrical systems come online, and the locomotive's onboard computers perform a series of checks to verify that everything is operating correctly. Only after those systems are functioning properly can the locomotive begin preparing for actual service. Then comes one of the most important systems of all, the air brakes. Unlike the hydraulic brakes on a car, freight trains rely on compressed air. Every locomotive continuously produces that air using an engine-driven compressor. While the train is parked, tiny amounts of air slowly escape through hoses, valves, and couplings. That's completely normal. No air system is perfectly sealed. As long as the engine is running, the compressor replaces those small losses almost immediately. But once the engine is shut down, the compressor stops too. Minute by minute, the air pressure begins to fall. Eventually, the brake system responds exactly as it was designed to. The brakes automatically apply. This isn't a flaw. It's one of the most important safety features ever developed for railroads. If a train loses air pressure because of a mechanical failure or a broken hose, it should stop, not continue rolling without brakes. The same principle applies when a locomotive has been sitting with its engine off. Before the train can move again, the entire braking system has to be recharged. That sounds simple. In reality, it can take several minutes for compressed air to travel through a long freight train. A train stretching well over a mile in length contains hundreds of feet of brake pipe and dozens, sometimes more than 100, individual rail cars that all need to reach the proper pressure before departure. Only then can crews perform brake tests to confirm that every car is responding correctly. On a busy main line, those extra minutes matter. Freight railroads operate on carefully planned schedules. One delayed departure can force dispatchers to hold other trains, reshuffle crews, or change meeting points farther down the line. The delay doesn't stay in one place. It spreads. A locomotive that refuses to start on time can affect trains hundreds of miles away before the day is over. That's why railroads often view idling as a form of insurance. Yes, it burns fuel. Yes, it produces emissions. But compared with the cost of a missed departure, blocked track, or stranded freight train, that fuel bill can be surprisingly small. And that's exactly how railroad managers tend to look at the problem. For them, the question isn't, how much diesel are we burning? The real question is, how much would it cost if this locomotive wasn't ready when we needed it?